In this video, we will study the Reflex Klystron, an important microwave oscillator, presented by Professor Gotapu Sasibhushan Rao. We will understand its working principle, the Applegate diagram, the concept of modes of oscillation, and finally solve a few gate examination problems. The central idea is simple. Velocity modulation, electron bunching, energy transfer, microwave oscillation. Microwave tubes are mainly classified into two types. The first is the O-type or linear beam tube. Here, the electric field and the magnetic focusing field are approximately parallel. The second is the M-type or cross-field tube. Here, the electric and magnetic fields are perpendicular. The klystron and reflex klystron belong to the O-type category. So, the reflex klystron is basically a linear beam microwave tube. What is a reflex klystron? A reflex klystron is a single-cavity microwave oscillator. It operates using velocity modulation and electron bunching. An important feature is the negatively biased repeller electrode. The repeller turns the electrons back toward the resonant cavity. Unlike the two-cavity klystron, here the same cavity performs both the modulation and energy extraction functions. So, the reflex klystron uses one resonant cavity plus one repeller electrode. Now look at the physical arrangement. The reflex klystron consists mainly of an electron gun, an accelerating voltage source, a single resonant cavity, a repeller electrode, and an RF output coupling arrangement. The electron gun produces the electron beam. The resonant cavity provides the RF electric field. The repeller is maintained at a sufficiently negative potential, so the electrons cannot reach it. Instead, they are slowed down, stopped and sent back toward the cavity. This return motion is the key difference between an ordinary two-cavity klystron and a reflex klystron. In this slide, we see the working principle of reflex klystron. Let us follow the electron beam step by step. The electron gun produces and accelerates the electron beam. The electrons then cross the gap of the single resonant cavity. The RF voltage across this gap changes with time. Therefore, electrons crossing at different instants experience different electric fields. Some electrons become faster. Some remain approximately at the reference velocity. And some become slower. This is called velocity modulation. After crossing the cavity gap, the electrons move into the repeller space. The negatively biased repeller slows the electrons, brings them momentarily to rest, and then reverses their direction. Because the electrons have different velocities, they do not all turn back at exactly the same time. During the return journey, the faster and slower electrons come together and form an electron bunch. The bunch then returns to the cavity gap. If it reaches the cavity during the proper retarding phase of the RF field, the electrons lose kinetic energy. That energy is transferred to the cavity field. This energy transfer compensates for cavity losses and sustains microwave oscillations. So remember the complete process. Velocity modulation, repeller action, bunching, energy transfer, oscillation. Now let us understand the Applegate diagram. The Applegate diagram is a distance versus time representation of electron trajectories. The vertical axis represents the distance of the electron from the cavity gap. The horizontal axis represents time. Electrons leave the cavity with different velocities. The faster electron travels farther into the repeller space before turning back. The slower electron travels a shorter distance and turns back earlier. The reference electron follows an intermediate trajectory. Now observe what happens during the return journey. The different trajectories gradually move closer together. This convergence represents electron bunch formation. So the important idea from this diagram is different velocities, different trajectories, trajectory convergence, electron bunching. Now we come to the important concept of mode of oscillation. For maximum energy transfer, the electron bunch must return to the cavity during the retarding phase of the RF field. The equation shown on the slide gives the optimum round-trip transit time of the electron bunch. Instead of reading the complete equation symbol by symbol, you can say, the electron transit time must be equal to 3/4 of a cycle, plus an integral number of complete RF cycles. That is the physical meaning of the equation. For the first mode, the transit time is approximately 3/4 of 1 RF period. For the next mode, one additional complete RF cycle is added. Therefore, different allowable transit times correspond to different modes of oscillation. The key point is, transit time decides the RF phase at which the electron bunch returns to the cavity. And that phase decides whether the electrons give energy to the cavity or absorb energy from it. Now let us apply the transit time concept to a gate examination problem. The problem gives the oscillation frequency and the mode of operation. We are asked to determine the transit time of electrons in the repeller space. The first step is to find the RF time period from the given frequency. You need not read the equation symbol by symbol. Simply say, the time period is the reciprocal of the operating frequency. Once the RF period is known, we use the appropriate mode condition. The mode tells us how many RF cycles are included in the electron round-trip transit time. After substitution, we obtain the required transit time in nanoseconds. Then identify the corresponding correct option. The important concept is that the mode number directly determines the electron transit time. Now consider this conceptual gate question. It asks why the transit time of electrons in the repeller space must satisfy the specified mode condition. The reason is related to energy transfer. First, the cavity produces velocity modulation. Next, the repeller reverses the electrons. During the return journey, electron bunching takes place. For continuous oscillation, the bunch must return when the cavity field is retarding the electrons. At that instant, the electrons lose kinetic energy. That lost energy is transferred to the RF field in the cavity. Therefore, the correct physical statement is, returning electrons give energy to the gap oscillations. That is why the transit time or mode condition is so important.